Elon Musk's continued refusal to reveal critical specifics hasn't stopped Tesla's factories in Texas, Nevada, Berlin, and Shanghai from quietly reshaping their production lines for a vehicle that could rewrite everything we assume about low-cost electric transportation. The rumored Model 2, projected to debut at an unprecedented $11,799, is poised to disrupt the EV market more aggressively than any prior Tesla launch. Yet the company remains unusually silent about the details. This raises an obvious question. Why avoid discussing it openly? And how is Tesla achieving what legacy automakers consider impossible? Building a fully capable EV at such a price? The truth becomes clearer when examining Tesla's real manufacturing timeline, a timeline far more advanced than the company suggests. Patent filings from September 2024 outline what Tesla refers to as an unboxed assembly system, a production method that discards nearly half of the traditional steps by allowing multiple sections of the car to be built simultaneously, only merging near the end. Instead of the usual 300 to 400 sequential tasks, Tesla's internal documents show roughly 160 parallel steps, slashing build time from the industry norm of 20 to 25 hours down to about 10. Supplier information further reveals a structural battery pack acting as the vehicle's floor, which eliminates countless chassis components. Unlike the Model Y structural pack, the Model 2 uses a cell-to-pack layout with no modules, reducing part count by around 370 pieces and cutting costs by $1,200 to $1,800 per car. At the same time, logistics data contradicts Tesla's public claims that Texas will be the primary production hub. Tooling shipments between October 2024 and January 2025 show that Shanghai and Berlin have already begun gearing up for simultaneous production alongside Texas. This indicates that Tesla plans a multi-continental launch from day one to avoid supply bottlenecks, balance global demand, and prevent rivals from filling regional gaps. Even paint shop permits reveal details Tesla hasn't shared, showing that early units will use an in-mold coating technique, allowing only a few basic colors at launch, likely limited to white, black, and silver. Beneath the manufacturing strategy lies the deeper question of how Tesla can realistically reach the $11,799 price point, and the answer is hidden in the Model 2's component architecture. Regulatory documents point to an enhanced LFP chemistry blended with manganese for a modest energy density boost of roughly 15%, while remaining cheaper than nickel-based chemistries. Supplier agreements show 35 GWh of this chemistry, reserved specifically for a vehicle matching the Model 2's battery needs, enough for more than 500,000 units annually if using roughly 66 kilowatt-hours packs, a figure larger than Tesla's public estimates. Meanwhile, Tesla's energy division has been quietly testing aluminum-lithium hybrid cells at Giga Texas, achieving around 310 W/kg and extremely rapid charging, 10% to 80% in around 12 minutes under 350 kilowatts DC. These cells aren't production-ready due to cycling stability issues, but could dramatically reduce costs by late 2026. Beyond the battery, rare earth import data confirms that Tesla has dropped permanent magnet motors entirely for an externally excited synchronous reluctance design, eliminating rare earth metals and reducing costs by several $100s with only a slight efficiency hit. Interior materials shift to a low-cost engineered polymer textile, cheaper than Tesla's vegan leather, but durable enough to meet standards, though with noticeably different feel. Electronics follow the same philosophy. A unified single-board computer replaces Tesla's usual distributed system, reducing wiring by about 60% and saving several $100s at the cost of reduced long-term computational headroom. Thermal management also becomes simpler, with a single cooling loop controlling battery, motor, and cabin systems through electronically actuated valves. While cheaper and lighter, this system may struggle in extreme heat above 105 degrees Fahrenheit or cold below -4 degrees Fahrenheit. Conditions common in several U.S. states, and Tesla has not published detailed degradation curves accounting for this. These engineering and cost decisions feed directly into the question of who the Model 2 is actually meant for. Homologation data classifies it as a subcompact, under 170 inches long, under 68 inches wide, and with a wheelbase below 104 inches, making it smaller than a Model 3 and closer to a Mazda 3 or Honda Civic. Despite Tesla's marketing as a compact family car, Its rear legroom of about 33 inches trails even a Toyota Corolla, and its cargo space of 11.5 cubic feet is far below the Model 3's capacity. Even charging performance is trimmed. Its peak rate tops out near 170 kilowatts, not the 250 kilowatts capability of the Model 3, adding several extra minutes to long-distance charging sessions, an important factor in large states like Texas or Florida. Tesla also adopts an iPhone SE-style product plan with virtually no customization, no performance version, no upgraded interior, no extended range model, and only limited color options. Warranty terms shift as well, with an 8-year or 100,000-mile battery warranty guaranteeing 70% retention, slightly lower coverage than the Model 3. Insurance analyses suggest another trade-off. The structural battery pack means underbody damage is more expensive to repair, possibly raising insurance premiums by 12% to 18% compared to similar gasoline vehicles. None of this signals deception from Tesla. Rather, it represents strategically selective communication designed to spotlight milestones while downplaying complex engineering realities. For buyers who want the full picture, understanding these hidden factors is crucial to making an informed decision rather than relying on simplified marketing narratives. Tesla is quietly reshaping its factories in Texas, Berlin, Nevada, and Shanghai while staying silent about the real progress behind its upcoming low-cost EV, often referred to as the Model 2, expected to launch at around $11,799. This car is designed to challenge the entire market, yet Tesla has released almost no official details. Internal filings reveal a new unboxed assembly method that cuts nearly half of traditional production steps, allowing major vehicle sections to be built at the same time and reducing manufacturing hours dramatically. Supplier documents show the use of a structural cell-to-pack battery design without modules, lowering costs and part counts while improving efficiency. Shipping and tooling data also confirm that Tesla is preparing multiple factories for simultaneous production rather than a single location start. These hidden decisions, combined with simplified materials, compact dimensions, and limited early customization, show that Tesla is building an affordable, globally scalable EV while publicly keeping expectations controlled. Rather than replacing craftsmanship, the system elevates it by removing the mind-numbing tasks that traditionally cause fatigue and errors. But machinery alone does not fully explain why Tesla is pulling ahead. When comparing this line's performance to Ford's F-150 Lightning production, Volkswagen's ID.4 factory, or GM's Ultium-based EV operations, the differences become staggering. Tesla's daily output nearly triples Ford and more than doubles Volkswagen, and its cycle time from raw chassis to a completed Model 2 is only 7.5 hours, almost half the industry's 12 to 14-hour norm. Faster assembly doesn't translate to shoddy construction. The exceptionally high first-pass yield shows the opposite. These quality improvements mean fewer calls, fewer early service visits, and greater long-term reliability, all of which translate into stronger resale value and higher customer confidence. Material usage is so efficient that scrap rates fall below 1%, and energy usage per vehicle drops nearly 20% compared to traditional EV facilities. Water use in stamping and painting is also significantly reduced, lowering both environmental impact